Hello there, Physics 30. Welcome to Magnetism Lesson 6. Alrighty, so we're going to get into, at the bottom of this page here, current can be induced in a conductor if the conductor is moving through a magnetic field. Same hand rules, thumb points in the direction of the movement of the wire, applies. Okay, so what's happening here is what we're going to do is we're basically going to have, I'm going to draw this out for you guys so you can get a better understanding of what they're talking about, is let's say that we have a magnetic field going into the page. Alright. And I'm going to put a wire going through that magnetic field. So let's put a wire going through the magnetic field, and it looks like so. All right. Now, in that wire, naturally, there are electrons. All right, there are electrons. Okay. And so right now, the electron's not moving. There's no current at all. There's none. It's just sitting there. It's a wire. It's not attached to a battery or anything, but it's just in a magnetic field. Right. So what we're going to say, though, is that what happens when I decide I want to move this wire in this direction? If I move that wire to the right, I'm going to get this electron is now moving to the right. And what we know is that a moving electron in a magnetic field creates force, right? If you have a moving charge, it gives force. So even though this electron's in a wire, it is still moving to the right. And so what's going to happen is there's going to be a force on this electron, right? So if I think about it, if I have my thumb in the direction of the electron and the fingertips going down, my force, right, my force on this electron is going to be this way, right? And what's going to happen is that there is many electrons in here, right? There's many electrons in this wire. Now, what's going to happen is that they're all going to experience, whoa, that's a highlighter, that's not what I wanted. They're all going to experience the same force, right? And so we're going to get a current, right, where the electrons are actually flowing, even without a battery, just by moving the wire perpendicular to this, okay? Same idea is if I decided to move the wire this way, okay, if I move the wire this way, then the electrons are then, in theory, moving this way to start. They would also have velocity this way. And now, instead of going to down, they would go up, right? And so if I move them to the left, then they would move that way. Move them to the right, they would move this way. And so what I'm doing is I'm moving the entire wire within a magnetic field, and I'm creating current. Now, this is interesting. If I can move the wire and create current, so if I move the wire, the current is creating moving electrons. So I'm actually making electricity just by moving a wire through a magnetic field, right? You're creating electricity by moving a wire in a magnetic field. That's awesome, right? And so if you think about it, if I got this, now your thumb, that's a little bit different. Your thumb is going to point in the direction of the movement of the wire, because that's the way the wire is moving. And so your thumb should point in the movement of the wire, and then your fingertips in the direction of the magnetic field, as always, and then your palm points in the direction of the force. So in the first one, for A here, right, your thumb should be pointing this way, and your fingertips should be pointing up to the sky, which tells you that the force, right, the force would be in that direction. And we're using our left hand, so we're going to talk about conventional, we're going to talk about just regular electrical current, not conventional current, right? And so therefore the current would be in this direction, right? The current is in that direction. All right, and we can do the same thing with the second one. Now our thumb's pointing to the top of the page, and our fingertips are still pointing up to the sky, which means that the current, if we look at where our palm's facing, right, the current is now in this direction. Right, we're creating a current. If I change the direction, it would create opposite current. So now we've got to move the wire down. So thumb down, fingertips in. Sorry, guys. It's going to point this way. And the next one, thumb down, yeah, fingertips into the page. The next one, thumb to the left, fingertips into the page, and you're going to get a current that acts upwards. All right, so that's the direction of the current. And so we're creating a current. Now this is cool because in the concept is that you can create electricity basically in a never-ending loop, right? If you have a current, right, you have a loop around if you have a loop of wire inside of a magnetic field and you just start spinning that loop, it should create some kind of current nonstop, right? And so the loop creates, and so if you put a loop in a magnetic field and you move the whole loop, then the current creates this, and da. So that should, in theory, create eternal energy. The problem is that's not actually what happens, right? What actually is happening is we have to move the wire. As soon as the wire stops, we're not going to be able to do this, right? So we have to move the wire. So we're actually adding energy in. Now, this is a good idea, but if you think about it, so now if we have this whole going on, if we have what's called a wire, right? If we have a loop of wire, okay, in a magnetic field, it will generate electrical energy. So this is a really good idea, because what this leads to is that basically the invention of practical electricity is that, well, if we just have something that can constantly keep moving the wire, then we can constantly keep creating electricity, right? And this leads to basically the idea of a generator, right? It gives us a generator, and that's really all it is, okay? Is we have a wire or a loop of wire moving a magnetic field. And we have magnets naturally occurring everywhere, so we can use that, right? So you can use this to as problem 26. I'm just going to keep going here a little bit. All right, it's going to be a little longer video, but we're going to finish this off. All right, so what we're going to do here is we're going to have basically this concept of we're going to have something where we're going to put a loop of wire into a magnetic field, okay? And we're going to basically, this is known by Michael Faraday, and it's basically you can have a DC electric motor, all right, or you can have an AC electric motor, right? Okay, so DC electric motor is kind of what we're looking at here. Okay, the current flows in one direction. And what's going to happen is this is we're going to move this wire, okay? We're going to move this wire here. And once it starts to move in the magnetic field, if we keep moving it, it's going to create current that keeps passing in or out, right? And it's going to charge a battery. Now we have a split ring communicator, so that every time I move the wire to the other side, it keeps causing the current to go in the same direction. All right, so there's batteries and all sorts of stuff like that. Now this is not a lot of things like that. It's hard to see what's going on here, but basically every time that we pass over this split ring, we're going to change the direction of the current, which allows us to keep the current direct. All right, so this is a cross section of a DC electrical motor. Okay, a single loop of wire is made inside, and it looks like so. So what's going to happen here is by using our hand rules, and correct me if I'm wrong, but what's going to happen basically is this B is going to get forced that way, and A is going to get forced this way. All right. Once they go across, if you have a split ring, right, what would happen eventually is it would just end up being vertical, as the forces would just keep repelling and adding until it ends up being vertical. What happens is after it goes a certain direction, right, once it crosses that line, so this ball here is originally out, or into the page, once it crosses that line, we're actually going to switch the direction of the current, so that now it's into the page. And this one, which was originally into the page, now becomes going out. And so what's going to happen is then it's going to get forced around. And so it's just going to keep going around and around. And so this is essentially what electric motor is, all right? There's a major difference between electric motor and electric generator, all right? And I've got a YouTube video here. I hope you guys kind of see here. So what we have here is we have basically a permanent magnet. So this is a motor, right? A motor is where we're taking electrical energy and we're turning it into kinetic or mechanical energy, right? And so what happens is basically the loop has a permanent magnet, and we're just going to basically start this video here. Come on. Or not.
Of an electric motor.
Okay.
We can
so
see
what's
the
gonna
battery,
happen here is that
the commutator,
the battery
the brushes,
placed into
the copper wire loop, and the permanent magnet.
This motor. All right.
The brushes are attached to a wooden support, and the commutator is fixed to the loop of copper wire.
Okay, so the battery gets placed in.
The commutator rotates freely, rubbing against the brushes.
We change the direction of the battery, we change the direction of the spin.
Now, when we pass current through the circuit, this creates a magnetic field around the wire.
So these brushes. All right, so these brushes, I'll just do it over here. Is basically we have this split ring. Sorry. We have that loop of wire, but that loop of wire is attached to what's called a split ring. So it looks like this. All right, so a ring that isn't quite fully connected. Okay, and then up on the top and on the bottom, so you can complete the circuit, is called brushes. So the brushes just kind of touch the edge of the ring. The brushes touch the edge of the ring. And so what it is that then this ring can spin this ring can spin, and as it spins, it's going to have that change in direction of flow, which is what we wanted, right? So that direction of flow, because then it's going to keep everything going. Now, this is a pretty complicated theory, but you kind of picture it with me, is that every time that this goes 180 degrees and we change the current direction, it's going to allow us to basically have the next 180 have a force. And so this split ring communicator, or commutator is what they can call it, is it allows us to switch the electron flow, which allows the motor to keep running, right? Otherwise, it would just go to a single spot and be stationary, okay? So
which interacts with the
motor,
field of
right?
the permanent magnet to produce a rotation of the loop that looks like this. The electric motor and the electric generator are related like two sides of a coin.
So it still has
in general, the task of an electric motor is to convert electrical current into mechanical force.
If I want a generator,
on the other hand, an electrical generator converts mechanical force into electrical current.
All right. And this is super cool.
So as you can see, we can simply rearrange our motor into a generator.
Energy turned into electricity, and then by having a motor,
in this case, we will provide the mechanical force with the
one thing you should notice there, the magnet got moved. It was just moving out of the way so we could add this little wind turbine.
Windmill rotor attached to the loop and connect a bulb in place of the battery.
Right, we're going to have
we will leave the magnetic field as it is.
This would actually just charge the battery.
Right. And as the wind rotates the blade, an electrical current is produced.
Now we're going to induce current. We're going to create current, which is going to cause that light bulb to light up. All right. Feel free to click on this video. They do explain it a little more. Skip the first 30 seconds, just a guy talking. All right. So what is the main difference between motors and generators? Well, the main difference is that motors convert electrical current into mechanical force, and generators convert mechanical force into electrical current. All right. One thing I want you to note is that basically every generator works on the same concept, where we're spinning a wire within a magnetic field. All right, if you spin a loop of wire within a magnetic field, you're going to get to current. All right, so it doesn't matter if it's a generator used at home or a generator as in the size of the Sheerness power plant, where they're burning coal, they're using the steam to spin a turbine. Okay, this is another basically a term for a turbine. Turbine has a magnetic. Turbine can sometimes be the opposite, where they have a magnetic field that's spinning inside electrical, but that really doesn't change anything. All right. So just keep in mind that generators convert mechanical force into electrical current, and motors convert electrical current into mechanical force. All right. So then we get electromagnetic induction. Okay. So this is pretty cool, where now we have the opposite. So if we have basically Michael Faraday and John Henry thought, well, if we can create electric current in a magnetic field, what about a magnetic field being created by electric current, or electric current being created by a magnetic field, right, and going back and forth? And so they basically have this idea that you can read through this, but basically they have this idea where by moving something back and forth very quickly, you can create multiple currents, all right, moving a magnet. And so what they decided to do is, and now you can finish your practice or your anticipation guide, you should be done your practice problems at this point, all right, is they said, well, what if instead of us moving the wire, what if we moved the magnet, right? So in the previous example, we moved the wire, right? We took the wire and we moved it across a magnetic field, right? And that gave us current, okay? That gave us current. Now what we're going to do is and it gave us DC, direct current. Now we're going to move a magnet. So now we're going to move the magnetic field past a wire. And what's really cool is that what actually happens is the wire itself will create a magnetic field that repels the motion. So if I have a north and I'm bringing it towards, the wire wants to stop that from happening. It wants to resist it. And so it'll actually create a north end and cause a current that does that. As I'm pulling it away, okay, it doesn't like motion. It wants to stop motion. So if I pull this away, it's going to create a south pole, which is this concept of it trying to pull that back. So if you're pulling away, it's going to pull it back. Then we switch the magnet, right, if we were to bring it close, right? And so what's happening is, what I want you to notice is the current. So the current kind of points the direction. So in this way, when it's doing this, the current is going this way, is going to the right. Then when I move it away, the current starts to go to the left. And so we're going to get what's called alternating current, or AC. Right? And so this is Lenz's law. An induced current flows in such the direction that the induced field opposes the action of the inducing field. Right? So whatever the magnet is doing, it wants to do the opposite. Right? If the magnet's approaching with south, it wants to push it away using a south. If it's going away with a south, right? I'm just talking about this example over here. Okay, if it's going away with the south pointing towards it, it wants to induce a north. So that does this. And so then we get this idea that if I'm going to continuously do this, move this magnet towards, then away, move it towards and away, I'm going to get this current that goes this way, then this way, then this way, then this way, right? It's going to go back and forth, back and forth, back and forth. And that's that alternating current. All right, and what they found is that it's easier to actually move a magnet than it is to move the wire. And so this is what leads to turbines, all right? Turbines are a little bit more magnetic. Now we can use the wire and all that stuff, but basically it's the same concept. Generators, turbines, anything that creates electricity is based off this idea that we have some kind of wire, some kind of magnetic field, and they're moving through each other, okay? And either way you do it, you're gonna get some kind of current, whether it's alternating or direct, doesn't really matter, right? Okay, so this is where the term AC/DC comes from, right? You guys, well, probably most of you heard that music, or some of you, AC/DC, right, is alternating current and direct current. It was on the back of a typewriter, I think, is where they got the name from. All right, so anytime we move any kind of wire or any magnetic field, moving them separate or together across each other perpendicularly, we're going to get induced current. All right, that Lenz's law is basically that the induced current flows that the induced field is created opposite, opposes the action of the inducing field. All right, this can be seen now. I showed some of you guys this eddy tube demonstration, and so what I did there in class, and this was, I think most of you are gone, you can watch some videos on this, is I basically set up a copper tube, right, and I dropped a magnet into the copper tube, and I dropped a magnet that was outside. Now, what's going to happen is this magnet is going to fall very fall due to gravity, right? This magnet, though, is going to fall slower, all right? It's going to fall slower, right? This will take, let's say this takes 1 second, this will take 2 seconds, right? Now, the reason that happens is because of Lenz's law. Now, I've got a magnet here, and let's just call this south and this north. As this falls in, I have a tube. Now, remember, this is like a coil, right? A tube is essentially a coil, right? Electrons can flow around it. As this happens, the tube is going to create a magnet, right? A magnetic field that's going to oppose the motion. All right, so it's going to oppose the motion. So it's going to create a magnetic field. Now, this isn't actually really a magnet, but it's going to create one. It's opposing the motion, right? Okay, so it's going to oppose the motion that way. As the magnet falls to the tube, it's going to slow it down, right? Ooh, let's get back to my regular color here. Right, so if the magnet's actually in the tube, right, this is the electrons flowing around the tube, and the magnet's in the tube, and I have a south and a north on this magnet, right, and I'm just showing you a circle, so that's the neodymium ring I dropped. It's going to still create a magnet, except one part, the bottom part of the tube, is going to create this magnet, right, south opposing south and north at that end, and this side wants to pull it back up, so it's actually going to create a south and a north because it wants to pull it up, because if it's falling away, it's going to do the opposite. So as it goes through these magnetic fields, right, these magnetic fields that are induced, right, because of the electrons flowing, so this green is caused by electrons flowing, flowing around the tube, it's caused by electrons flowing, is going to cause it. And so what I can do is I actually have basically this concept of where it's actually going to fall slower because there's a magnetic field acting against it, right? And so we have this whole thing, and this leads back to that levitation thing, right, where we're having some kind of gravity in this case. It's still falling through, right? Fg is still larger than Fm, right? And you guys can try this at home. If you have any kind of copper tube around at all, and you have a magnet, any kind of magnet will actually work, you just might not notice it as good, is if you drop the magnet through the copper tube or any kind of conducting tube, it should slow down, right? It's a very interesting phenomenon. All right, so again, this is just basically explaining what I'm saying here. All right, you can click on this. The link didn't work great for me. This is a very strong magnet. All right, and it's going to fall very slowly, right? The stronger the magnet, the stronger the induced tube would be, or the induced magnet would be, so it'd slow it down even more. All right, if you want to use this to the next level, you can actually watch this video, and you'll see that actually what's happening is the magnetic field, he has a coil here, right? And the magnetic field and electric field interact so strongly that it actually starts to create, and it's actually you creating energy that's going to cause it to melt these magnets. It's very, very cool. All right. So there's a couple things to do. This is just to end chapter 12. We're going to compare forces and fields. So there are similarities and differences between gravity, electricity, and magnetism, right? So they're all forces. They're all forces and fields that act at distance, right? Gravity, electricity, magnetism, none of them need to touch in order to cause a force, all right? That's what's unique about them, all right? Each force and field gets weaker the further you go from the source, right? The farther you get from Earth, the less gravity. The farther you are from a magnet, the less gravity, less force, and the farther you are from the electric field or the electric whatever charge, the less electric force you have. And none of the three fields require a medium to transmit the field or force. That's important, is that there's no medium. I don't need to have air in order for gravity to happen. I don't have to have anything between two magnets. It can just be empty space, and I can still have a force. The reason that's important is because this leads us into the understanding of how does light work? What is light, right? How does light come from the sun to the earth? There's no medium, right? But it's energy. And so we're leading into this whole idea. Okay, there's some differences. Gravity requires mass, electricity requires charge, and magnetism requires moving charges. Remember, magnetism is all about moving charges. All right, it's just moving charges lining up. Okay, you'll also notice the gravitational field is always inward, whereas electric field can be outward from positive charges and inward from negative, and magnetic fields are always charged, closed loops moving around charges, right? So there is some differences, but that's pretty much it. Alrighty, so that is the end of chapter 12. This is really important, this whole medium thing, this concept they don't need a medium, because that leads basically into the discovery of what a photon is and how it works. And we're going to see that in chapter 13 and 14. All right, that's in chapter 12.